Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and in this video, we'll look at support vector machines. So this is going to be an extension on the intuition that we built up on kernels before we started on past 4 project videos. So here we'll talk about roughly these topics: hyperplane, what is maximum margin classifier, then support vector classifier, support vector machine, etc., and see how the how this intuition all plays out in this video. For references, I've listed 2 references here. One is the Introduction to Statistical Learning, Chapter 9, and Chapter 7 from Pattern Recognition and Machine Learning. So, what is a hyperplane? So as we can imagine on this particular plot, let's say we have these orange data points and we have some green data points that we need to separate these 2 classes. So we can draw lines, straight lines through each of through this plot so that we can separate this. So here are 3 lines that we can draw, and there could be infinite number of lines. So each of these lines that we are drawing here could be called as a hyperplane. So in general, the dimensions is one less than the dimension of the data set. So if we have here we have a 2-dimensional data set, so the hyperplane would be 1-dimensional and hence a line. If it's a 3-dimensional data set, hyperplane would be a 2-dimensional plane. Then what is a margin? Now, margin is uh, as shown here in this particular plot. Let's say this is the decision boundary. We have the solid line that separates the orange data points from the green data points, and then we look at the closest data point on of each of those 2 classes to the decision boundary. So in this case, this particular point is closest to the decision boundary, and on this side these 2 are the ones that are the closest one. So the middle ground, so the line that we can draw between those 2, between these sets of closest point right through the middle, will divide the space into 2, and so each of those space is shown here by magenta arrows, and those are the margins. And the dotted line then is the again the margin hyperplane, or that is also a decision that could be thought of as a soft margin, as we'll talk later on. So margin is uh, nothing but this space that's around the main solid decision boundary that we have. So what's the intuition behind a maximum margin classifiers? And so, as we saw before, we could draw hyperplanes in various positions. And so, if we draw hyperplanes as shown in this particular case, the leftmost figure, we see that the margin is there, which is a very narrow margin because the dotted lines are very close to the solid line. Same thing in the middle figure, we do have the separation of classes, but then the margin is too tight. So the solid line is very close to the dotted lines there. And what happens in this case is if there are new data points, then the margin has to shift drastically to accommodate that new data point to the correct class. And so the another idea then is to generalize to have ability to generalize more to a new data set. What we want is a margin that um, that is such that it's we can get the maximum space of separation between the 2 classes. So if we look at the figure on the right, we see that this is the max. We get a maximum separation between the 2 classes if we draw this solid line right through the middle of uh, these 2 green dots and this one orange dot. And so we do have the dotted line shifted far away from the solid line, and thus we can, in this position, we get the maximum width or maximum margin. And so the classifier that tries to classify data points using this approach is called as the maximum margin classifier. And again, in maximum margin classifier, as we saw, this idea of maximum margin can be built up more on what is called as a support vector classifier. So in support vector classifier, the idea for the word support is tied to these data points that are associated with this dotted line. So these are called as the support vectors. So these two green dots and that orange dot is the support vector, and it's called a support vector because uh, that dotted line is built based on those points for each of those classes. Now, for support, one advantage of support vector classifier is, as we talked earlier, if there is a new data point, then uh, as shown here, this entire decision boundary has to shift. As we saw in the previous case, this was the decision boundary. Now we are right here. And so this creates an issue of generalization when new data comes in. And therefore, there is an idea of a soft margin. And what the intuition behind that is, we can allow the points to be on the wrong side, and we can still keep the same decision. So if there is a data point that's new data point comes in, and if it's on the wrong side, that's okay. uh, we do not have to shift our decision boundary substantially. What we can do instead is add a penalty to that particular data point, so that uh, it can be so it will have certain weight of misclassification. So as we can see in this particular plot, this green dot is on the wrong side, so it's on the orange side, and it's away from this decision boundary, and that's also the solid line. So the penalty shown here by this Greek letter zeta is greater than 1. So the farther it is in this direction, the greater would be the value of this particular penalty. And similarly, this orange dot on this side is on the wrong side, and so again the penalty for that would be greater than 1, and it will continue to increase if it goes farther and farther away from the decision boundary on the wrong side. And here the magenta dot, the magenta outline, this green dot, is on the correct side of the decision boundary. It is classified as a green dot. However, it is still within the margin of classification, is inside the dotted line, and therefore there would still be a penalty on that, but it would be a smaller penalty because it's correctly classified. It's just that it's within the boundary. And in scikit-learn, we can change how flexible we want, how much uh, uh, how much of misclassification we want to allow. We can set that by parameter c, as we'll see. And if the data points are on the right side of the class, so green dots such as shown here, or the orange dots such as shown here, then those would, the zeta value for those would be 0. So there's no penalty for those because those are correctly classified data points for each of those classes. And here we can see the value of y is 0 for the solid line, and then y is equal to +1 for this upper margin boundary, and then we have y is equal to -1 for this lower one. So this we are calling it as a positive class, and this we are calling it as a negative class. Now, as mentioned earlier, we can tune how much of the misclassification we want to allow. So how much data points we think would be okay if they are on the wrong side, and that can be set by a parameter c. So if the value of c is large, then we get a larger margin. So the distance between these two dotted lines would be much larger, and so there will be more room for the data points to stay on either side, but still the value of zeta would be much lesser. So we are kind of allowing the data points to be where they want, and still not care about adding too much penalty on them. But as we start to reduce the value of c, we see that this margin becomes narrower, and then with a small margin there is indeed a lesser tolerance for misclassification, or lesser tolerance that the data points would be on wrong side of the margin. Now, what support vector machine is, then it builds upon all those ideas and introduces or adds a new capability of kernels. Um, as we have seen in the previous video on kernels, the central idea with using kernels is that, let's say you have a data set that's in two dimensions that cannot be separated in linearly, or that cannot be separated. Then what you do is you take you add a dimension to that data set, project it in a, let's say, two-dimensional data set into three-dimensional data set, and they're using kernels, and then you'll see that the points magically separate into, maybe some points stay higher up and some points stay lower down. So then the higher class and lower class could be easily separated in that dimension. So that's the general idea. If you're still not sure about how kernels work, I suggest checking out the video on kernels. I think it was about 4 or 5 videos back. So here what we have is, on the left hand side we have a data set. We still have two classes, the orange dots and the green dots. However, in this case, the green dots are with kind of sandwiched between the orange dots on either side, and so if we use a linear classifier, then it's not able to separate this. So if we draw a straight line, this we could draw a line like this, or like this, or either way we cannot clearly separate the green and the orange dots. So the solution to solving this type of classification problem is using a line that is not straight. So using a non-linear line. And in the figure in the middle, you can see that if you use a polynomial kernel, then we have this line which is non-linear. It has curved line, and we could separate these orange dots and the green dots as shown here. Another variation of another type of kernel, which is also commonly used, is the radial basis function based, so radial kernel. And what that does is, it would clearly separate these green data points from the orange data points as shown here. And that's possible because they would use the nonlinear boundary to separate those two classes. And while so far we have talked about support vector classifiers, now let's talk about support vector regression on this slide. So we have talked about this briefly in the previous videos. So the idea is that we are looking at a epsilon tube, which is shown here in the blue shaded region. So if we have data points which are black dots that are shown here, then the main idea is that we want the data points to be within this epsilon tube. If they are within this epsilon tube, then there is no penalty associated with those data points. However, if the data points lie outside epsilon tube, then there is a penalty associated with those data points. So as you can see, the letter zeta here, she is equal to 0 if the data points are above this orange line in the middle and still in the epsilon tube. However, if the data point is outside, such as on here, then for that data point there will be a penalty and the zeta value would be greater than 0. Similarly, if the data points are below this orange line, then it's marked by zeta star still equal to 0 because they are within the epsilon tube, that is this blue shaded area. And however, if they are outside that, farther away from that, then as you go farther away, the value of the zeta star would increase. So we are adding more and more penalty for that particular data point, which is away from the existing data points within this epsilon tube. Now, the types of kernels that are used in the scikit-learn for support vector machines are shown here. We have a linear kernel, we have polynomial kernel, we have RBF, radial basis function, we have sigmoid kernel, and these are the equations that are shown for all these types of kernels. And this angle bracket just shows that it's a dot product between x and x transpose. And this is for polynomial, we have this degree that we can use. So you can use a nth, second order, third order, fourth order polynomial based on how complicated the data is, and how much of wiggle room you need to separate classify those data points. And then we have the RBF that we saw, and we have the sigmoid. Now, how does the RBF kernel work? So let's start from the figure on the right hand side here. If we have these data points that are the orange data points, right? One is right there. There are a couple here, and we have the green dots that are sandwiched within those orange data points. Now, if a new data point comes in, let's say this magenta data point, and we need to classify that. So how would RBF classify? How would RBF work? So if we look at the radial basis function that's shown here in the top, uh, if a new data point comes in, which let's say it is x star, then based on that we can think of the test observation as x star is equal to x1 star, x2 star, xp star, and then the trend observation would be equal to xi. And now if we calculate the Euclidean distance between this data point and this data point, we can calculate it by this formula. And if this Euclidean distance is very large, for example, in this case, the distance between the magenta dot and the x1 orange dot would be much larger. If you have a large number, then when you put that number in this expression, when you try to get an exponential for that, when calculating the kernel, then that value would be very small, and the value for that data point would be very small in the kernel. And so essentially this particular data point would have no effect in flipping the sign of this decision function to classify this as a positive or negative class. So the most effect would be from the closest point, that is here, to so this point would dominate what the sign of the decision sign of the output of the decision function would be. Would it be positive or negative, to assign that data point to either a positive or a negative class. So that's kind of the general intuition of how the RBF work, RBF kernel would work. And I've put a reference below if you want to read further on this topic. Now in scikit-learn, there are different implementations for SVM. We have for classification and regression, we have SVC, linear SVC, new SVC, and then for regression, we have SVR, linear SVR and new SVR. Now the new SVC and new SVR, it's uh, a version where there is a parameter new instead of C, and that controls the regularization that's within the um, uh, function. So that's the change. And with one class SVM, this is generally used to find outliers, and so that's a separate method that we have available. The types of kernels that we can use with each of these methods. For linear, we just have the linear method as we would expect. However, for all other methods, we can use all the four types of kernels that we saw earlier. In addition, we can use a pre-computed custom kernel, custom kernel. So if you have a specific kernel, so let's say you have a data set that needs to that can be easily classified only and only if it can be uh, transformed into a specific dimensional shape by using a specific type of kernel that you have custom made. Then we can also use that kernel to along with each of those methods listed here. And this is the actual run of these different kernels and different methods that I wanted to share. And here we have these blue data points, and within those is sandwiched this red data points. And if we try to separate them by either of these methods, this RBF method was very good at cleanly isolating those data points in middle. Polynomial, this was I think around 9 degree, and still it was struggling to get those out. Linear models were definitely, this problem was out of reach, and they are not able to classify those two different classes. And similarly, if we increase the distance between these classes, I thought maybe that will give some different effect. And the radial basis again was able to classify the polynomial kernel. uh, Maybe it was getting closer to classifying, it did get some of the points as compared to here, but then still uh, in this particular scenario, uh, it was difficult to separate them using polynomial as well. Now, the support vector classifier and support vector regression. So if we want to get some mathematical intuition, this is not a derivation. I'm just going to walk through the equations that are listed in the docs and uh, um, try to talk about what those equations could be telling. And here, the for each of those two types, we have this minimization problem where we have W transpose W that we have seen before, and here we have the regularization term with C and zeta. So zeta is again the distance for how far they are from the decision boundary, and then C is the regularization parameter that can be used to control how much penalty we put, how much penalty we allow to be put on the misclassified data points. And similarly here we have the same setup, except that we, instead of just one zeta, we have zeta I plus zeta star I, and that's because we are looking at the space above and below the epsilon tube as shown in the figure below. Whereas in case of the classification task, we have a different situation where we are interested to keep things out of the margin, whereas in regression we want to keep things inside the margin. So that's the difference there. And these minimization equations are subject to these constraints that are shown here. And so that can be reduced to this particular minimization problem, which is alpha transpose q of q alpha minus E transpose alpha. So here the alpha is the alpha represents the dual coefficients for the data points, and the Q is the kernel as shown here. And same thing on this side for regression, except that now we are taking a difference between alpha and alpha star, uh, and we have these additional terms on the right hand side for this minimization task. And these again are subject to these conditions that are listed here. And the final decision function then looks like this. So where I is in support vector. So this uh, is only this for these calculations we are considering only support vectors, because the value of alpha for all non-support vectors would be 0. And so that just makes the computation easier as well. So we have yi alpha I k, k of xi x plus b. So b is the intercept, and we have the same equation on this side, except that we are taking a difference between alpha minus alpha star in on for when we are talking about the regression. And how then the values that we talked about can be tuned or tuned in Scikit-learn's method. So if we look at the support vector classifier method SVC, this is what you'll see when you look at what parameters could be uh, input into this particular method. Then the C is the C that we have here, the regularization parameter. So you can set a value for that. So if you are doing a grid search CV or cross validation, you can put a range of these values to kind of change the width of the margin, and then allow change the threshold of misclassification for each of those data points. And then additionally, with the kernel functionality, you can change the type of kernel, you can change the, if you select a polynomial kernel, you can change the degree, you can change the, also again based on the type of kernel, you can change the gamma value, you can change the coefficient. So all these functionalities allow kind of to fine tune the fit that you would need for classifying a particular data set. Similarly, for regression, we have similar functionalities as we have seen before. But here, in addition to that, we also have a value for epsilon that can be tuned. So with the value of epsilon, we can, as you saw before, that would control the epsilon tube within the fit. And going further, there are additional functionalities that can be used, which is related to sample weight and class weight. So the class weight is as shown here, which is now let's say we have two sets of data points, so the orange data points here, and which are large majority, and there is a very small number of or green data points that need to be classified. Now here, if we if with and without class weights, it could make a difference to get a correct decision boundary between those data points. So what the class weight allows is we can give a more or less weight depending on which class is a majority or minority in the data set. In addition to using class weight, and this can be given as a dictionary input when we are setting up the model. And sample weight is another version. So instead of giving weight for each class, here in case of sample weight, we can set a value for each sample or each row of the data set. And so then each data set, each sample or each instance would have its own weight that would be then used while performing the fit to find the optimal hyperplane that separates the class or finds the best regression fit. And class width is available for, of course, the classifiers. So SVC, new SVC, linear SVC, and the sample weight is available for all these methods using that is both classification methods as well as the regression methods, and also the one class SVM that you could use to find the outliers. And here are some tips from the docs, major tips. There are more in the docs if you want to read through. The one is to check if the input data is C ordered continuous. And so the reason for that is if it is not, then what a scikit-learn would do is create a copy of that. And so creating that copy is going to take much larger space if the data set is much larger. And so if you don't want that, what we want to make sure is check if this is C ordered contiguous. Forgot to put how to do that. So there is command in numpy that can do that. Next, depending on what type of hardware you're using, the RAM size could be changed for cache. So if you have more RAM, then you could set the value for cache size to be higher, and so that could expedite the fitting process. The value of C, if the data is noisy data, then what you could do is add more regularization, and so you could decrease the value of C. That is, you're reducing the width or reducing the margin, and so it's the tolerance is a lesser tolerance when we are trying to classify the data points. And very important, when working with support vector classifier, support vector machines, you definitely want to scale the data so that the data is either between 0 and 1 or -1 and +1. So that's very important. And finally, here is a code snippet which is standard. I have the data set, and if you are using a regressor such as linear SVR, then you create a variable reg, fit it on trend set, and then call it for prediction on a test set. So that was it for this video. I hope in this video you got an intuition about what support vector machine is and how it can be used for the tasks such as classification or regression. And we talked about kernels. If you need more intuition about how kernels work, suggest checking out the videos. I think on the 5th video before this particular video. And in the next video, we'll work on a 5th project in the series that we have been working on. And the reason is because that project would be difficult to be solved by just linear methods, and that's where we can see a huge difference a support vector machine can make to solve that type of problem. So I hope to see you all in the next video. Please like, share, and subscribe. Thank you.